I'm just saying.
All right, how's everyone feeling? Any questions or concerns or needs before we get started? All right, in that case, we've been working on rotation for the past week or so. Last time we went over centripetal force and acceleration, talked about what they were and how they are not the same as centrifugal force. And today we're going to be talking about a different way that force can cause rotation. I at least introduced the concept at the tail end of last lecture before we were to discuss it today. The concept for today is that of torque. Now, who's heard that word before? Before I even said it. All right, good, just checking. Where do you tend to hear that word come up in common enough English? Like where, in what context have you heard that word spoken? Sports, yes, there's definitely a lot of torque in sports. Cars, very good. Those are easily, in my opinion, the two most common places that torque is discussed. And I bring this up to try to mention that, to try to bring into your mind that torque is a very common sort of thing. Common enough that people actually talk about it. I do try to teach this class from the perspective of the stuff that you see and use every day. And I'm going to continue that with torque because sports and cars, as often as those are involved in our daily lives, aren't even the most mundane, common places you tend to see torque, because you use torque every time you open a door. And that is what we will be analyzing today, what torque is and how it affects common life on Earth, like everyday interactions on planet Earth. Pictured on the screen right now, I think of this as a door as seen from above, and someone is exerting a force on that door to try to make it spin, because that is usually the point of a Western-style door with hinges. You want it to rotate out of your way so that you can then step through the opening. The purpose of torque is to cause angular acceleration. This is to contrast with linear force that causes linear acceleration. Throughout this chapter, I've mentioned the differences and the similarities between linear motion and angular motion. We've compared delta x to delta theta, compared v to omega. We haven't done any math about it, but linear acceleration has a counterpart in angular acceleration. We're not doing math for that though, so you don't need to know that variable. I'm just bringing it up as context. Things can accelerate while they spin. All these things I consider counterparts to one another. They cover the same basic principle, it's just one is about straight lines and the other is about spinning. There's loads of these counterparts between all forms of linear and angular motion. Turns out most things in the linear world have an angular counterpart. And that also includes force. The angular counterpart to force is called torque. And this is in reference to the purpose of torque as it compares to the purpose of force. The purpose of normal old-fashioned linear force is to cause linear acceleration. You push on something because you want it to change its motion, either speed it up or slow it down. That's the purpose of normal linear force. But this type of force and this type of acceleration only point in straight lines. So if you want a door to start spinning on its hinges, you have to exert that force in a very specific way to generate torque instead. Because the purpose of torque is to generate angular acceleration. I promise everything in this formula will make sense later. I'm just kind of setting the stage right now. But again, force and torque are counterparts. Their function is to cause acceleration either linearly or angularly. If you want to make something start spinning, you have to use torque to do so. And to generate torque, you just have to use linear force in a very specific way.
And again, you do this subconsciously every day. When you approach a door with hinges, what do you tend to do to it? Open it, but how do you do so? Sorry, let me ask it like that. What do you do to open a door with hinges?
Twist the knob.
All right, you specifically are applying force on the doorknob. I'm going to try to not use the door too much because that's not on camera. Instead, I'm going to use this meter stick as a very bad analog. So let's say this is the door, seen two-dimensionally, and my hand is going to represent the hinges of that door. So this is the hinge. Where's the doorknob in relation to the hinge? Other side. Again, not a trick. Doorknob is always on the opposite side of the door as the hinges. That's on purpose. Because even if you don't grab the doorknob, you do tend to grab the side of the door that the knob is on, and you tend to apply force on this side of the door, and it starts rotating. That is the secret recipe for torque. You are exerting force at a distance away from the hinge, from the fulcrum, from the axis of rotation. Those are all synonyms in this case. In order to generate torque, the force you apply has to be some distance away from the pivoting point. And that's again why the knob is on the opposite side as the hinge. If you've ever tried to open a door by applying force near the hinge, it's not an easy experience. I'll use the door itself here for this part. If I grab the far side of the door, it's not difficult. It's an old, pretty heavy door, so it takes some force. But if I exert the same amount of force here, not a lot happens. I'm probably using more force and getting less output. And that's because if I exert the force here, I just happen to generate less torque. And that has to do with the formula for torque, seen right here. Torque, symbolized here with a lowercase Greek tau. It's not a T because we use T for other things and we have to be specific around here. Tau, torque, equals radius times force. If you want to make something spin, you have to exert force on it some distance away from the point you want it to start spinning around. So the R in this case is the distance away from the pivot point that you are applying said force. We still call it a radius because you can still think of it as the radius of a giant circle. If you let a door swing 360 degrees, the length of the door is the radius of that giant circle, so that's why we still call it radius. So, if you want to make something spin, you got to exert torque on it. To exert torque on it, you exert force on it a distance away from whatever point it is going to start rotating around. If you exert the force very close to the axis of rotation, not a whole lot happens. If you exert the force very far away, you get more torque, therefore the object should be more easy to begin spinning. Conceptually, how's this formula feel for right now? Okay, slight nodding, slight thumbs up. You do this sort of thing every single day. You have a deep down conceptual understanding of this, even if you've never put words to it or put numbers to it before, because again, you do this subconsciously every time you open a door, be it a building door or a car door, because they all have hinges. But it comes up in loads of other places too. This is one of the most common physics things that simple machines humans have built utilize. It comes up in cars, for example, because the purpose of a car is for the engine to output force and energy and work to make the wheels spin. And in order to make the wheel spin, you have to exert torque on the wheel, because you have to exert torque to make everything spin. So once again, here we have the bike tire. In order to make this wheel start rotating, I need to exert force on it, so I'm going to grab it right here on the edge of the wheel and exert force on it. Note that the spot where I applied that force is a distance away, literally a radius away, from the center of the wheel. And so my force applied at that radius from the axle generates torque and causes the wheel to start spinning, because torque causes angular acceleration, like how linear force causes linear acceleration. And that force has to be applied some distance away, or you don't get any torque. If I, instead of exerting a force here, if I instead exert force directly on the axle, which would be a radius of 0, because if I'm acting on the axle, the distance from my force to the axle is 0. Does that make sense? If I act directly on the axle, will the wheel ever start spinning? No, I'm just causing it to accelerate linearly, the old-fashioned way. If you act directly on the axle, the object will just linearly accelerate because you're using linear force on it. But if you exert a force a distance away from that axle, your force turns into torque and you get the rotation you're looking for. Again, you have to do this every time you want something to spin or start rotating. Cars will do this by, usually the wheels are mounted to the actual output shaft in some way, shape, or form, some distance away from their center. Frankly, even an axle bolted straight through the middle, that axle still has some radius, and so that force is still being applied some distance away from the center. But you don't even have to have an engine to use torque to make a wheel spin, because if I just roll this thing along the ground, there's torque involved in that too. Because notice, right now, I am actually applying a force to the center axle, because that's where my hand is. If I'm just rolling this wheel the old-fashioned way, the force I'm applying is on the axle, radius of 0, so I'm not actually myself generating any torque right now. There's a different force acting, at a distance away from the center, and ironically, it's friction from the road. If the wheel tries to spin this way, friction points that way, and that is a force some distance away from the fulcrum, and that causes it to spin, which is why it only does this when it's touching the surface. If I just move the axle around when not on the surface, it doesn't spin. So every wheel relies on torque, regardless of whether it's connected to a car engine or not. Bless you. Does that all sound good so far? All right, now the other place that we mentioned, that you guys mentioned hearing about the word torque is in sports. And it is true that torque is involved in sports because, as it turns out, most sports are somehow applications of torque. Torque and impulse, those are the two main things in sports. The biggest place where you see torque in sports is if the sport involves some sort of implement that you are hitting something with. For example, a bat, or a racket, or a golf club, or technically even if you're just using your leg as a swing arm to kick something, there's still torque involved in that. If a baseball is flying at me and I swing a baseball bat at it, note the force between me and the ball, which really is the force between the bat and the ball, is being applied at a radius away from my hand. So I am generating torque and hitting the ball with the torque rather than with my bare fists, which tends to work better. The use of a tool like this tends to kind of multiply your force output in a way. By using torque, by using a longer lever arm, you get more force at the end of the object than you could just generate if you were punching with your bare fist, which is why baseball batters don't tend to punch the ball into the outfield. I probably tried that at some point in Little League and it didn't end well. But again, any game that uses an implement like that is an application of torque. Even volleyball, where you're using your arms as a lever arm, rotating about your shoulder. Again, your legs count too when you're kicking something because they spin about your hip. But it's not just sports. It turns out most human tools use torque, including our earliest ones. Wheels use torque, hammers use torque, because again, that's a heavy thing attached to a stick, and you generate torque by swinging the thing on the one end of it, which is why using a hammer tends to be better than just punching the nail into the wood. Again, I tried that too as a kid, didn't end well. But yeah, most human inventions use torque in some way, shape, or form. So pretty much every tool, be it sports equipment or not, you can use this formula on it somehow. And I will now give a little bit of practice context for that, but before that, any questions? All right, so let's look at a tool designed to make something spin, because that's all a wrench is. It's just a tool to make the bolt rotate. Here we have a 1 meter long wrench, and we are going to apply a force of 12 newtons on the end of it to try to make that bolt spin. So let's say that this here is our wrench. The radius is going to be the length of its handle. We are going to physically grab it here and exert force right there on the end. Torque equals radius times force. So how much torque do we generate using this wrench? 12 Newton. Yes, I'm just now realizing I didn't read that part out loud. Sorry. So torque, radius times force, radius of 1 meter times the force of 12 newtons, does give us an answer of 12 Newton meters. I'm going to actually tab back to point at this part more directly. Information about the variable of torque real quick. Torque is symbolized by the variable tau, again because the letter T is used for other things, both upper and lowercase. It is still a vector, technically speaking, but rotational vectors are kind of weird. Instead of pointing forwards or backwards, they only ever point clockwise or counterclockwise. Those are directions for rotational vectors. We'll talk a little bit about that later. And the unit for torque is Newton meters, which is literally newtons times meters, because that's what you multiply together to get the answer. We never gave it a dedicated one. It's just force times distance, newtons times meters. So that's its unit, and that's where it comes from. So yes, in conclusion, we generate 12 Newton meters of torque using this wrench. Sound good so far? All right, now to start changing things, what happens if we instead use a longer wrench? Specifically twice as long. With a radius of 2 meters.
6 newtons. No, it'd be 24 newtons.
Yep. Because the formula is radius times force. So if you double the radius, you're multiplying by 2 instead of by 1. And the amount of torque that that produces doubles. And you don't actually have to work any harder. You're using the same amount of force, but you're getting twice the torque, meaning that that bolt is twice as likely to start spinning just by using a longer wrench. How about the inverse? What happens if we cut the length of the handle in half?
It'd be 6.
It would. So instead of 1 or 2, we make it twice as short, so half a meter, 0.5 times 12 newtons, gives us only 6 Newton meters. So by using a shorter wrench, you're kind of accidentally making the whole process harder on yourself. The same force generates less torque if the handle is half as long. So in general, you get more torque not only if you use more force, sometimes you do just have to use more force to get something to start spinning, but you also get more torque if physically the lever arm is longer. So if you're ever having a hard time getting a bolt or a screw to start rotating, just get a longer wrench and or screwdriver. That's why if you've ever spent much time around like any sort of auto or mechanic shop or even a plumber's office, you probably noticed wrenches of drastically different size. I swear I've seen monkey wrenches with 1 or 2 meter long handles. You use those for the really awkward bolts that just don't want to spin. And it does work with screwdrivers as well. Physically, the longer the screwdriver handle, the easier it is to get even a screw to start rotating. Conceptually, how I feel so far. Okay. Now, I guarantee that you have noticed this sort of thing before, even if you've never thought about it consciously. I'm going to mention another tool that's designed to help make things spin, that being a crowbar. The purpose of a crowbar is to get a manhole cover lifted up. These things are heavy, because it's a giant pizza made of cast iron. Of course it's going to be heavy. If you have ever tried, like foolish 8-year-old me, to lift one of these yourself, it doesn't usually end well. Typically, one of the easier things to do if you need to get one of these things moved is to try to only lift one side of it, basically using the other end as a fulcrum and kind of try to rotate it up and slide it out of the way. That's how most people lift these sorts of things. But it's still a heavy slab of iron. It's not going to go super well. And this is why crowbars were invented. If you're just using the length of the manhole cover as your radius, as your lever arm, you're only going to generate so much torque. But by introducing a crowbar, your radius suddenly gets longer. And now you're applying force here, and it's more likely to get this thing to start rotating, and then you can slide it out of your way. So again, that's why those were invented. Most tools do this to some extent. And if you don't believe me, if you've never felt this yourself or never thought about this yourself, I can simulate this effect for you here in the room. This is a 2-meter stick. It's 2 meters long. This is a clip that is sized to slide onto a meter stick. And it's got a little hook on it so that I can hang this 1 kilogram weight from it. Now, when you hold the stick like this, your hand is basically acting as a fulcrum. The stick can rotate about that spot. And that means that the weight of this item is generating a certain amount of torque right now because there's a force of gravity acting on this spot at a radius away from my hand. So this is generating torque. If I leave it alone, it would start spinning. So as evidence that there is torque here. And in order to hold it up, I have to be exerting an equal amount of torque to keep the stick from spinning. Does anyone want to hold this for themselves to see how much torque is currently acting in this system? All right. So you just want to hold it right there on the end. About how much effort do you feel like you're exerting right now?
If we have to like hold it here.
All right. Now, what I'm about to do is slide this mass further down. You are allowed to add a second hand if you feel you need to. As I slide the mass down, its weight doesn't change, but the radius from the fulcrum does. And we feel the need to add a hand. Would you say that you're exerting more effort now? A lot more. Yeah, that's about 10 times the distance, so this weight is generating about 10 times as much torque right now. And it's only going to get worse if I continue to slide it down. So, testimony from your classmate, does torque increase with radius?
Yes.
Yes. Thank you. You can feel this for yourselves if you like. If you don't want to today, that is fine. Lab in 2 weeks will utilize the same basic thing, so look forward to that. Torque definitely increases with radius. There's a quote attributed to Newton that says, if I have a lever arm long enough, I could move the earth, which is true. If you had a meter stick the length of the solar system, a very small amount of force could move the earth on the other side of it. It's very impractical, but it's theoretically possible. Of course, a meter stick that big would have its own gravity, and that's a discussion for another day. Point is, torque is real. It increases with both force and radius. Use longer wrenches and screwdrivers. Sound good so far? All right. Now, there's one other place where torque is applied that we're going to discuss for today. And so far we've kind of looked at torque as the thing that makes stuff spin. If you want something to start rotating, you have to exert torque on it. But sometimes you don't want something to spin, correct? There are times where you don't want something to be rotating. That might be true of a seesaw or any sort of a balancing system, like old-timey pan balances, where you would have a certain amount of thing hanging from this side, a certain amount of thing hanging from this side, and you want them to be level, like on a scale. Sometimes you don't want seesaws to rotate sometimes, you don't want cranes to rotate sometimes. Basically, the tilting arm of a crane uses torque to rotate it into a certain place and then lock it there. But once it's in position, you don't want it to spin anymore. There are loads of times you don't want something to spin. And in order to prevent rotation, you have to make sure that all of the torques acting on something are balanced. We've been referring to what happens when net force equals 0 in relation to Newton's first and second laws. When net force equals 0, objects don't accelerate. They're considered to be in equilibrium, and they're just going to keep doing what they're already doing. So right now, all these stationary objects on my desk, the net force acting on them is 0, and they don't accelerate. Same basic principle applies to torque as well. If you don't want something to be rotating, you have to make sure that the net torque on it is 0. Because torques can add up like forces do. Torque is the angular version of force. And if you want something to remain stationary without spinning, all the torques acting on it must add up to 0 and cancel out. If net torque is not 0, you get rotation and angular acceleration. But if net torque is 0, you don't get acceleration. I've got this balance seesaw thing currently pictured, so I'm going to try to show what's happening with the torques here. I've currently got 2 items pictured on either side of this thing. Let's say that they both have the same mass, just like 10 kilograms, for example. They have the same mass, and they are currently sat equidistant from either side of the fulcrum. This little triangle here represents the fulcrum or the pivot point. That's the balance spot that everything wants to be level around. That is the point of rotation. And I've placed these 2 objects of equal mass at the same distance from the fulcrum on purpose. In this situation, there are 2 torques acting on this thing that point in opposite directions. The torques point in opposite directions. Before I address that, my preceding question is, what forces, normal linear old-fashioned forces, are currently acting on this object, on the balance itself, on the actual teeter car?
What forces?
Yes, what forces are currently acting on the seesaw, the plank, the platform?
The two blocks and the triangle.
All right.
So, force of gravity on both doors.
Very good. Each box has its own weight that points down. Those are downward pointing forces on this on the seesaw itself. And you are correct. In order for this thing to not be moving, there would also need to be some normal supporting force from the fulcrum. So if this thing is totally level, the normal linear force on this thing must all add up to 0, which means the weights of the two boxes and also the support force from the fulcrum do have to all add up to 0 and cancel out. So that's the old-fashioned way that we've looked at this, linearly speaking. But now I also want to look at it rotationally speaking. My first question is, do you think that this normal force here, acting from the fulcrum, physically holding up the seesaw, do you think this is currently generating any torque? Does this force make any torque right now? Why not?
Because the net torque is 0.
The net torque is 0. There are still torques acting on it though. Kind of like how there are forces on all the stuff on my desk. There are torques here that are going to cancel out. My question is, why is this force not currently generating any torque? It actually has to do with the formula. The formula for torque is torque equals radius times force. What is the radius between the fulcrum and the normal force that the fulcrum exerts? 0. All the force in the world can't generate any torque if it's acting on the axis of rotation. This normal force could be 8 million newtons, but it will not generate torque if radius is 0. So this force is incapable of making the balance beam spin. That force is not generating any torque right now. Which leaves the weights of the two boxes as the two forces currently generating torque on this object. Because they are both acting 1 meter away from the fulcrum. So none of the forces on the fulcrum are ever going to generate any torque, because if you're acting on the fulcrum, your radius from the fulcrum is 0. Again, it could be 8 million newtons, but if radius equals 0, torque equals 0 as per that formula. So this can't generate torque, but these two can. And in order for this thing to stay level, those two torques have to cancel out. Which means that these two torques point, they do end up having the same magnitude, because these two boxes have the same mass, therefore they have the same weight, and they are acting at the same magnitude of radius from the fulcrum. So as per the torque formula, there's two torques here with the same strength. Does that make sense? Same force at the same distance generates the same strength of torque. But they still cancel out because the torques themselves end up pointing in opposite directions. Again, the only direction that an angular vector can point is either clockwise or counterclockwise. And even though the forces both point down, they're generating opposite direction torques. What direction is this weight trying to make the swing arm spin in? This is the radius. The force is acting down. sometimes it helps if you want to physically take like a pencil or something to do this. If you take a balance beam and you exert a downward pointing force on the right side of it, what direction does the whole thing start spinning in relationship to a clock? Clockwise. This torque, this weight on this side of the beam is currently generating clockwise torque. But on the opposite side, the same direction of force generates counterclockwise torque. Makes it spin in the opposite direction. So these two torques have the same strength, but since they point in different directions, they add up to 0. Same as, net force on an item being 0, therefore it doesn't accelerate. If net torque is 0, it doesn't rotate. And so if you as a kid ever played that game of you and your siblings or your cousins trying to get the seesaw at the playground to stay totally level, I'm not the only one that did that, right? All right. If you ever played that game, that's what you were trying to do there. You were trying to make sure that all of the clockwise torques on one side canceled out with the counterclockwise torques on the other. You were trying to make sure that they all added up to 0. So, math out of that old game. All right so far? All right. To give you one or two small formulas, they're technically the same formula, about how to use this if I were to ask you a different math question about such a balance beam. If you want something to be in rotational equilibrium, all the torques acting on it must add up to 0. So you would have to take stock of what forces on that object are generating torque, how much torque they are generating, and making sure that all the torques add up to 0 once you factor in clockwise versus counterclockwise. You can think of it as either net torque equals 0, or alternatively, all the clockwise torques equaling all the counterclockwise torques. They mean the same thing, it's just whatever your preference is. Now, to apply this to a sample question, just to get some practice work into your notes. Excuse me. We're basically going to look at a different seesaw, but rather than the two masses on either side being equal, I have imbalanced them. Again, these kids are playing that game I mentioned, where you want the balance beam to be level. Except these two kids don't weigh the same, because most humans don't weigh the same. In this case, we've got a 30-kilogram kid sitting somewhere on the left side, and a 60-kilogram kid sitting 1 meter away from the fulcrum on the right side. Now, conceptually, before I do any actual math on the board, where do you think kid 1 needs to sit in order to balance this thing, given your understanding of torque? To the left. How far on the left?
2 meters.
2 meters. Very good. Conceptually, you already understand what's going on. I'm just now going to show how to calculate it in case you ever need to know that. So we're going to calculate definitively where kid 1 needs to sit to prove that they are generating equal and opposite torque as kid 2. So we're going to prove that the net torque here equals 0, or try to find in which scenario it will equal 0. There's going to be 2 torques acting on this thing. There's the torque generated by kid 1, and then separately the torque generated by kid 2. So sigma torque, the sum of all the torques, is going to be torque 1 plus torque 2, and again, for the balance beam to remain level, it must add up to 0. formula for torque is radius times force. So kid 1's torque is going to be kid 1's radius times kid 1's force, which is going to be the weight of the kid. I want to make it absolutely clear. On a seesaw like this, it's the weight of these two people that is acting as the force. Mass is not force, but weight is. So I will further specify FG1. Kid 2 is going to generate torque based on their radius and their weight. And again, these two torques must add up to 0. Feel okay arriving at this position? All right. Now real quick, I'll just show calculating the weight of each child. So kid 1, mass of 30 kilograms times -10 for G, strength of gravity on Earth. Kid 1 weighs -300 newtons. Again, mass is not force, so I just want to make that distinction. Kid 2, they have twice the mass, so they will weigh -600 newtons. Bless you. Ow. So again, these are the actual forces they're exerting. Yes?
So, why did the kid have to be like 2 meters, like to the side in order for
Precisely. You've worked ahead of me. Congratulations. I'm just going to prove that that is where this is going. So, we know the weight of each person. We want to know R1. We do already know R2, so we're just going to prove what R1 should be. Leave R1 blank. Force 1 is the weight of kid 1. Again, weight is the force, mass is not the force. We have to add that to the torque that kid 2 is generating. Kid 2 is sitting at 1 meter, and they weigh 600 newtons. Again, still has to add up to 0. So R1 is our only unknown. We are good to try to solve for it. If I simplify this a little bit, we could write it as a -300 R1 minus 600, as 1 times -600 is just -600 equals 0. I'm running out of board, so I'm going to take this next part over here. -300 R1 equals positive 600 if we move the -600 from left to right. Therefore, R1 should be 600 over -300, which would give us a radius of 2 meters. The negative just means that it is in the opposite direction as the 1 meter for kid 2. I wrote in positive 1 meter for kid 2. The positive in this case implies to the right of the fulcrum, and kid 1's -2 implies 2 meters to the left of the fulcrum. So, 2 meters is absolutely correct. If you jump straight to that number, you already have a good understanding of net torque, even if you've never thought about it before. How you guys feel? All right. I got a couple last things I want to mention. Very brief closing notes before we wrap up for today. First thing I want to mention is there's a piece of this formula that I haven't drawn explicit attention to yet, and that is this that is this perpendicular symbol attached to the radius. In the work formula, we have a parallel symbol because the work and the direction and the displacement need to be parallel for the work formula to work right. Here it's kind of the opposite. To generate torque correctly, the force has to be perpendicular to the radius. In practical terms, what that means is, if I want to open this door and the radius of the door's length is in the x-axis, I would have to exert a y-axis force to get this to start spinning, right? If this was in my hand and I asked you to make it spin, you would think to grab it and act either up or down. That is perpendicular, right angle, to the x-axis length of the stick. If I asked you to make this spin, would you ever think to try pulling it to the right? Would that ever make it spin? No. Good. That's because a rightward force is not perpendicular to the length, it'd be parallel to it. And that can never generate torque. Does that make sense? Same is basically true for a door. Well, to apply to the actual door, you'd never want to pull out on the hinges, you'd want to pull into its physical length. So again, something that you've noticed before, even if you've never described it. Last thing I want to talk about, the couple balance beams I've shown you guys tended to be balanced like this, where the fulcrum is exerting a force upwards at the same spot it is acting, therefore it's not generating any torque. But what about this situation? Does this make sense as something that could physically happen?
Yes.
Yes. It can physically happen. I can actually show you real quick. Again, lab in 2 weeks, we'll do this, so keep this in your memory bank. I'm going to try to replicate what's basically happening here. We've got a force of gravity applied on all the way on one end, and the fulcrum is very close to that end rather than being in the middle of the stick. And behold, it does level. How does this work?
Just the radius is there on the other side that just kind of counteracts with the weight.
Yeah, this is a very small radius, so this weight's not actually generating that much torque. It'd be a lot more torque if it was a lot further away. So there's not a lot of torque being produced on this side. The question is, though, what is on the other side making torque to counteract it right now? Because in order for it to not rotate, the torques have to add up to 0. That means there has to be a second torque over here to cancel this one out. So what is the thing making torque over here? Gravity acting on what? The weight of the stick itself. Yeah. When you balance a stick like this in the middle, again, it's 2 meters long, so I'm going to balance on the 100 centimeter line. The fulcrum is under a point called the center of mass, sometimes called the center of gravity. And basically that's like the one spot where all of the mass of the meter stick can be treated as. And so, the force of gravity acting on this spot doesn't generate any torque right now because it's acting at a radius of 0 from the fulcrum. If the center of mass is directly on top of the fulcrum, the weight of the item doesn't generate any torque. But if I move that fulcrum, the weight of the item is now at a radius, and it does generate torque. Again, something you've probably noticed before. If the stick isn't totally level, it just falls. Because again, there is now torque on this side, its weight is acting on its center, and there's nothing counteracting it on the other side of the new fulcrum. So this all has to do with a concept called center of mass, alternatively center of gravity, they're synonyms. And Friday, we'll be discussing that, along with a few principles along with the related concept of moments of inertia and angular momentum. And that'll wrap up our rotation stuff this week. Questions? All right. You know if you need anything, please have a wonderful day.
You have lab physics service, right?
Yes, lab this week, lab today, if you're in the Wednesday section. But not next week, though.
I won't be here for that.
Okay, yeah.
Sorry.
Yeah.